Researchers have long proposed using directed energy weapons or lasers on the battlefield. However, unlike regular kinetic weapons like bullets and missiles, little efforts have been put into developing this technology. It also doesn't help that these weapons tend to be less effective in certain environments or weather conditions. But it seems defense giant Lockheed Martin has finally cracked the code. The company recently unveiled DEIMOS, a laser weapon that can destroy targets with pinpoint accuracy and insane speed. DEIMOS can be mounted on ships, jets, or tanks, providing security for troops. But what makes this new laser stand out from other conventional weapons, and how will it reshape the battlefield in the future? The concept of using directed energy as a weapon can be traced back to the early 20th century with the advent of powerful radio waves and the discovery of nuclear energy. However, it wasn't until Theodore Maiman's invention of the laser in 1960 that the practical development of directed energy weapons became feasible. Initially, research focused on chemical lasers, which generate high-energy beams by exciting specific chemical reactions. In the 1970s, the U.S. Department of Defense began investing in chemical laser programs, developing systems like the Mid-Infrared Advanced Chemical Laser, MIRACLE, and the Atmospheric Propagation Laser. These early chemical laser systems were massive, requiring extensive facilities and complex support infrastructure. Despite their size and logistical challenges, they demonstrated the potential of directed energy weaponry by successfully engaging targets such as rockets, drones, and missiles during testing. The 1980s and the 1990s saw a shift towards solid-state lasers, which offered increased compactness, efficiency, and reliability compared to chemical lasers. The Strategic Defense Initiative, known as Star Wars, drove significant funding and research into directed energy weapons technology, including the tactical high-energy laser and the airborne laser programs. In the 2000s, advances in fiber optics, solid-state laser technology, and beam control systems led to more compact and efficient laser systems. The Joint High-Power Solid-State Laser Program developed a 100-kilowatt solid-state laser for potential applications in air defense and counter-rocket, artillery, and mortar systems. Concurrently, the development of high-power microwave weapons gained traction. HPM systems generate intense bursts of electromagnetic energy that can disrupt or damage electronic systems without causing physical damage to structures or personnel. Programs like the Counter Electronics High Power Microwave Advanced Missile Project explored using HPMs for non-kinetic strike capabilities. In recent years, the US and other nations have continued to invest in directed energy weapons research and development, driven by the potential advantages of these systems, such as precision engagement, bottomless magazines, and reduced logistical footprints. The U.S. Navy has deployed the Laser Weapon System, LAWS, and the Optical Dazzling Interdictor, Navy Odin, on various ships for testing and evaluation. If you're enjoying the video so far, be sure to hit that like button and subscribe for more awesome military content just like this. The U.S. Army has also made significant strides with programs like the Mobile Expeditionary High Energy Laser and the Indirect Fires Protection Capability High Energy Laser, designed to provide mobile, ground-based air defense and CRAM capabilities using high energy lasers. While directed energy weapons offer unique capabilities and potential advantages, they face several significant limitations and disadvantages that have hindered their widespread adoption and operational effectiveness. One of the primary challenges is the impact of atmospheric conditions on the propagation of directed energy beams. Clouds, dust, smoke, and other atmospheric particulates can absorb, scatter, or deflect the energy beam, reducing its intensity and effectiveness over longer distances. This atmospheric disruption limits the effective range of directed energy weapons and introduces variability in their performance, making it difficult to achieve desired effects on targets consistently. Another major limitation is the substantial power requirements of laser systems, particularly high-energy lasers. These weapons demand vast electrical power to generate and sustain their energy beams, which can be a significant challenge in mobile or remote environments. Generating and storing this power often requires large, complex, and logistically demanding support systems, hampering the mobility and deployability of laser platforms. Even when sufficient power is available, the intensity of directed energy beams decreases over distance due to natural beam divergence and atmospheric attenuation. This range limitation can be mitigated through advanced optics and beam control systems. Still, it ultimately imposes constraints on the effective engagement envelope of directed energy weapons compared to conventional kinetic weapons like missiles or artillery. Accurately acquiring and tracking tiny, agile, or maneuverable targets is another significant challenge for laser systems. Precise target acquisition and tracking are essential for effectively delivering the concentrated energy beam to the intended target. However, this cannot be easy to achieve, particularly in dynamic or cluttered environments. Even slight deviations in beam positioning can significantly reduce a weapon's effectiveness. While lasers are often touted as precision weapons capable of minimizing collateral damage, their effects can still cause unintended harm to nearby systems or structures, depending on the intensity and duration of the energy beam. This collateral damage risk can limit how directed energy weapons can be safely and effectively employed, particularly in densely populated or sensitive areas. As of now, several nations are developing countermeasures to mitigate the efforts of directed energy weapons. These countermeasures include advanced shielding materials, active protection systems, and jamming or spoofing techniques designed to disrupt or deceive lasers' targeting and beam control systems. As these countermeasures evolve, they could significantly diminish the operational utility of laser systems in specific scenarios. However, after years of research and testing, defense giant Lockheed Martin has built a directed energy weapon that can function effectively regardless of the environment or weather conditions. DEIMOS, short for Directed Energy Interceptor for Maneuver Short-Range Air Defense System, represents one of the most advanced and capable directed energy weapon systems developed. It is a ground-based, mobile laser weapon designed to defend against various threats, including uncrewed aerial vehicles, rockets, artillery, mortars, and incoming cruise missiles. At the heart of DEIMOS is a 50-kilowatt fiber optic laser, which serves as the primary directed energy source. Fiber optic lasers offer several advantages over traditional solid-state lasers, including higher efficiency, better beam quality, and more compact and rugged design, making them well-suited for mobile applications. The DEIMOS system is designed to be highly mobile, with the laser and associated subsystems integrated into a tactical vehicle platform. This mobility allows for rapid deployment and repositioning of the system to meet evolving threats and mission requirements. The vehicle platform also houses the power generation and thermal management systems necessary to support the high-energy laser. One of the DEIMOS key features is its advanced beam control and target acquisition system. This system employs sophisticated optics, sensors, and tracking algorithms to precisely acquire and track targets across a wide field of view. The system can simultaneously track multiple threats and prioritize engagements based on threat level, range, and target characteristics. The beam control system also incorporates advanced atmosphere compensation techniques to mitigate the effects of atmospheric disturbances on the laser beam. This includes adaptive optics to correct for turbulence and other atmospheric aberrations, and systems to monitor and compensate for the impact of factors like humidity, temperature, and aerosols on beam propagation. DEIMOS is designed to engage targets at tactically significant ranges, with the exact engagement envelope remaining classified. However, reports suggest that the system can effectively engage targets at ranges of several kilometers, depending on factors such as target size, aspect, and atmospheric conditions. In addition to its offensive capabilities, DEIMOS is equipped with advanced defensive countermeasures to protect against threats or countermeasures directed at the system itself. These countermeasures include active protection systems, hardening against electromagnetic interference or jamming, and other classified measures. Lockheed Martin has extensively tested and evaluated the DEIMOS system, including live fire exercises against various aerial and ground-based targets. These tests have demonstrated the system's ability to rapidly acquire, track, and engage targets with precision and effectiveness, even in challenging environments. DEIMOS represents a significant step in developing practical and effective directed energy weapon system for military applications. As technology advances, systems like DEIMOS are expected to play an increasingly important role in air and missile defense, counter-UAV operations, and other areas where the unique capabilities of directed energy weapons offer distinct advantages over traditional kinetic munitions. If you enjoyed the video, hit that like button, subscribe to the channel, and turn on the notification bell to stay up to date with our latest videos on military advancement.